In this video, we're going to investigate how derivatives have an impact on the shape of a graph. So suppose that we are dealing with some nice generic looking function like, I don't know, this guy right here. We'll call this y equals f of x. What we're going to do is try to determine what the graph of the derivative of this function would look like just based off of the general shape of the graph. So first thing we'll notice is that there are a couple of points on here that, according to what we defined a couple sections ago, would be considered critical numbers. Critical numbers are values of x where the slope of the tangent line is either equal to 0 or where the slope of the tangent line is undefined. Generally, those show up on smooth continuous functions as local maxima and local minima. Now, these two critical values will indicate that that's critical value in green. So critical value or critical number. An important question to ask is, if we are not at a critical number, if we want to figure out what's going on with the derivative, we need to classify slopes of tangent lines as being either positive or as negative. So on the first interval here, you'll notice that as we move to the right, we're moving in an upward direction. That indicates that any tangent line we would have along here would have a positive slope. So to the left of this, we would expect to see a positive value for the first derivative. In between the two critical values, I notice that the function is going in the downward direction, so any slope of a tangent line we would have in here would be a negative value. And then over here, any slope of a tangent line would be a positive value. Now, what these are trying to help motivate is the idea of what are known as intervals of increase and decrease. Intervals of increase and intervals of decrease. Now, for an interval of increase, if we want the original function to indicate that it's going in an upward direction, we would need that the slope of the tangent line is a positive value. Slope of the tangent line is calculated from the first derivative, and we want that value to be positive. For an interval of decrease, we would want the value of the tangent line, or slope of the tangent line, to be equal to a negative value. As such, if you can solve these inequalities, you will arrive at what we know as intervals of increase and intervals of decrease. Now, in the picture that's been drawn here, if I wanted to sort of set up a little line for what's going on in terms of f prime, I would note that at this value right here, we would have a value of 0. And at this value right here, we would have a value of 0 as well. That's the nature of the critical value. To the left of the first critical value, we see that this is positive throughout, indicating that that would be an interval of increase. In between, I see that the function is decreasing, therefore the slope of the tangent line would be negative throughout. And beyond that, once again, we see an increasing function, therefore the value of the first derivative would be positive. So what we're going to do is use a combination of calculus and algebra to figure out what this looks like for the first derivative, and then see if we can use this to come up with something that looks like this. Now, in order to do so, that involves solving a couple different kinds of equations and inequalities. So for critical values, we set the first derivative to be equal to 0. Once we have where it's equal to 0, everywhere that it's not equal to 0, those intervals are going to indicate where it's either positive or negative. So what we're going to do is use those critical values to create what we call test intervals. A test interval is quite literally an interval that you are going to be testing. So create an interval, or create intervals, using critical values. Wow, spelling is hard. Critical values as endpoints. So what you should wind up with is a whole bunch of open intervals that are separated at wherever you happen to see critical values. In this case, this would be 3 distinct intervals to the left of the first critical number, in between the two critical numbers, and then to the right of that critical number. Take a number from within each interval, plug a number from within an interval to the first derivative. If the first derivative winds up being excuse me, if the first derivative winds up being a positive value, then you have yourself an interval of increase. And if the first derivative winds up being a negative value, then you have yourself an interval of decrease. So with those things in mind, let me demonstrate how this process looks with a polynomial function. What I'd like to do is find the intervals of increase and decrease for f of x is equal to x cubed plus 6x squared minus 15x plus 2. Now to figure out intervals of increase and decrease, what we said on the previous page is we want the first derivative to be either positive or negative. First thing we really want to do, though, is figure out where we have those critical values. So to figure out the critical values, we're going to take the first derivative and set it equal to 0. So first thing we need to do is actually find that first derivative. We can differentiate each of these terms using the power rule. X cubed would become 3x squared. 6 times x squared would become 6 times 2x. Minus 15x would become minus 15 times 1. And plus 2 would become plus 0. Simplifying algebraically, we would have 3x squared plus 12x minus 15. Again, we're going to set this equal to 0 and try solving for x. To solve for x, I notice that we have a quadratic. As such, I am going to factor out a 3, and then continue to factor the resulting quadratic. For this quadratic, we're looking for two numbers whose sum is positive 4 with a product of negative 5. If the two numbers that pop into your head are 5 and 1, you're on your way. We also need the outer and inner terms to add up to something positive, so this will be x plus 5 and x minus 1. This lets me know that the two critical values are going to be at x equals negative 5 and x equals positive 1. We get that by setting these individual factors equal to 0. So I would set this up as, for f prime, at negative 5, we would have a value of the derivative that's equal to 0. Then at positive 1, we would have a value of the derivative that's equal to 0. So our goal is to figure out for these other three intervals whether we have an interval of increase or whether we have an interval of decrease. So with that in mind, we now have three test intervals to try out. They are from negative infinity to negative 5 to 1, and from 1 to infinity. So to test each of these intervals, to test negative infinity to negative 5, I need a number that is less than negative 5. I'm going to test x equals negative 10. What value you pick does not matter as long as it's less than negative 5. Now, when I plug this in, I can either plug it into the original derivative that we got back here, or I can plug it into the fully factored form. Either way should work out just fine. If I plug it into the fully factored form, f of negative 10 is going to be equal to 3 times x plus 5 would become negative 10 plus 5, and x minus 1 would become negative 10 minus 1. Now, I don't need to algebraically simplify this completely because the only thing that I need out of this is whether this quantity is positive or negative. So 3, that's a positive value. Negative 10 plus 5 is negative 5, that's a negative value. And negative 10 minus 1 is also negative. If I multiply positive times negative, I wind up with a positive value. It's going to give me something greater than 0. That allows me to conclude about this interval. It is going to be an interval of increase. It also lets me know that everything on this interval happens to be a positive first derivative. Now, to test the interval that is between negative 5 and 1, I can pick any number that's between negative 5 and 1. I would recommend anytime you can test this number, test this number. It is x equals 0. So f prime of 0 is going to be equal to 3 times 0 plus 5 times 0 minus 1. I don't need a calculator to tell me that that is a positive number times a positive number times a negative number, which is going to overall wind up being negative. That lets me know that negative 5 to 1 is an interval of decrease. Decrease, 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 all the way through this interval. And finally, to test the last one, I can pick any number that is greater than 1. The number that I am going to select that is greater than 1 is going to be 9001. I like testing 9001 because it's over 9,000. That gives us 3 times 9001 plus 5 times 9001 minus 1. I believe that that would be a positive number times a positive number times a positive number. Result is a positive number, letting me know that 1 to infinity is an interval of increase. Increase. So this lets me know that as far as intervals of increase are concerned, the two intervals would be from negative infinity to negative 5. I can either use a comma or a union there, depending on whatever notation I prefer, and 1 to infinity after that. For the interval of decrease, we would be talking about just negative 5 to 1. That also lets me know that the shape of the graph is probably going to be pretty similar to the graph that we saw on the previous page, just with some slightly different numbers, since this one was also increase, decrease, increase. This one is also increase, then decrease, then increase.